Hello world. Today we'll be discussing the derivation of Beer's law. My name is Carlington Sims and this lesson is intended to communicate a few concepts taught in AP Calculus. So let's examine derivation of Beer's law. Beer's law states that the absorbance is equal to the extinction coefficient times the concentration times the path length. Few concepts that you would need to know to understand this lesson are the absorbance, concentration, power, path length is sometimes denoted as L. I will be using B in this lesson. The extinction coefficient denoted by epsilon, and the constant of proportionality denoted by beta. So, a few terms that you would need to know to understand this lesson, or a few concepts that you need to understand to keep your results consistent. The absorbers must act independently of each other. The absorbing medium must be fully diluted in the interactive volume. The absorbing medium must not scatter the radiation, so it should not have any turbidity. It should have been sitting for a while before you run the sample. The incident radiation must consist of parallel rays, each traversing the same length in the absorbing medium. The incident radiation should preferably be monochromatic, or at least have a width that is more narrow than the absorbing transition, and the incident flux should only act as a non-invasive probe of the species under study. If any of these conditions are not fulfilled, there will be deviations from Beer's law. So let's look at the formula that we'll be using. States that the decrease in power, dP, is proportional to the incident power, P, concentration of the absorbance species, C, the thickness of the section, dx. Okay? So that's written out clearly here for you to see. Another concept, another way to describe what I just mentioned using a diagram is the decrease in power. If you consider this green arrow to be the initial power, it decreases as it goes throughout the interactive volume. In this first rectangular section, 0 to 25% of the path length has been traversed, and so forth and so on, 25 to 50%, 51 to 75%, and 76 to 100%. And I made the yellow rectangles fade to indicate that more and more of the path is being traversed. And also the power is decreasing as you go along that path. The little dots in here are supposed to indicate the concentration of the interactive volume. You can see that they're evenly spread out throughout the volume, which is supposed to be the case in your solution as well. And each of these little O's will have their own absorbance, and that is beta. That is our beta, the constant of proportionality. So beta is the constant of proportionality, and the minus sign in this equation indicates a decrease in power, P, as x increases. The rationale for saying that the decrease in power is proportional to the incident power can be described by a numerical example. If you start off with 100 photons and lose 2 by the time you reach the end of the sample, how many photons would you lose if you started off with 200 photons? with all else being consistent? Well, it's a simple relationship. If you started off with 100 and you lost 2, then if we started off with 200, 200 is just 100 times 2, so we would lose 2 times 2, and that would give us 4. So 4 out of 200 photons would be lost. So 4 out of the 200 photons would be lost. Okay. Another way of visualizing this is to imagine that you have different teams, okay? You have team photon versus team particle. Now, in this initial scenario, we have a certain amount of photons on team photon and a certain amount of particles, only 2 particles in our path length. So these particles can be considered our concentration, and these photons are our initial power. So as the photons move through the medium, the field, so to speak, then if we only have a small amount of particles, only a small amount of the photons would be absorbed. Okay? As we look to our second scenario, concentration 2, if we increase our particles, but we keep our photons the same, then more photons would be absorbed as they traversed the field, so as they move through the concentration. And in this last scenario, if we have even more particles, even more photons would be absorbed as they moved throughout the field. So we can see from the previous example that if the number of particles increase in the solution, that is, the solution becomes more concentrated, the solution does a better job of stopping the photons, so the absorbance increases. Let's see how Beer's law is derived using these concepts. Starting with the decrease in power is proportional to the negative constant of proportionality times the power times the path length times our change in x. Using some algebra, we can rearrange our equation by dividing by negative p on both sides, and so we end up with this equation. dp over negative p is equal to the constant of proportionality times the concentration dx. So this is the equation that we will be doing our integration from. It says that the limits of integration are such that P is equal to P naught, that's our incident power, at x equals 0. So this is P naught at x equals 0. That's the start of our sample. And P is equal to P, the remaining power, that's up here, at x equals b, right here, at the end of our sample. Okay? So let's work with the equations one side at a time. All right? On this page, we'll be working with the right side of our equation. So on this page, we will deal with the right side of our main equation. So our equation says that as we integrate over the limits of integration 0 to b dx, we can see that there's a 1 in front of our dx. And with that said, we can also recognize that any number raised to the 0th power is also equal to 1. So as we integrate over that range, we'll just use the integral power rule. Here is a reminder for the integral power rule. It says that the integral of xn dx is equal to x to the n plus 1 over n plus 1 plus c for n not equal to -1. So if we're going to be integrating from 0 to b, x to the 0 power dx, then we're going to get x to the 0 plus 1 over 0 plus 1. But that is simply equal to x to the first power over 1, which is simply equal to x. Now, as we continue with our equation, solving this equation, we're going to use the fundamental theorem of calculus. The fundamental theorem of calculus says that if we have the definite integral from a to b f of x dx, that is equal to the integral of f of b minus f of a. So when we apply this theorem, we get our constant of proportionality times our concentration times x over the range from 0 to b. We substitute 0 in we substitute in our limits of integration for our variable, and we have our constant of proportionality times our concentration times b minus 0. That's just substituting in 0 for x and then 0 for and then b for x. So we substitute in our 0 for x and b for x and subtract like we did right here, okay? And that leaves us with our constant of proportionality times our concentration times b, because b minus 0 is b. So as we move on, we'll work with the left side of our integration. Now, this side, our limits of integration are p naught and p, and we're going to be getting the integral with regard to p here. Notice that we have 1 over p because p is in the denominator. So if we're going to find the integral of that, we just use the law that says that the integral of 1 over x dx is equal to the natural log of x plus c. So here we have the natural log of p over the range from p naught to p. When we substitute in, like we did for our fundamental theorem of calculus, substitute in p naught and p, we have the negative natural log of p, that's our first substitution, minus, okay, because it's a minus natural log here, the negative natural log of p naught, okay? The upper term, upper limit minus the lower limit. And that gives us, since it's a double negative, the negative natural log of p plus the natural log of p naught. Now, when we have a negative natural log of p, that's the same thing as saying the natural log of 1 over p. So we can put our p in the denominator, and we are left with the natural log of p naught over p as the solution to the left side of our equation. So putting these two sides back together, we get that the natural log of p naught over p is equal to the constant of proportionality times the initial concentration times the path length. This is where we are if we've solved both sides. So we're going to wrap this up with Beer's law. If we convert the natural log into log using the relationship the natural log of z is equal to the natural log of 10 log z, it gives us Beer's law. Okay? If I had the natural log of 10 here, but I divided both sides by the natural log of 10, so this is like a 1 here, and I have the natural log of 10 over here. We have the log of p naught over p is equal to the constant of proportionality divided by the natural log of 10 times the concentration times the path length. Beer's law calls the log of p naught over p the absorbance, and the constant of proportionality over the natural log of 10 the extinction coefficient. And so Beer's law says that the absorbance is equal to the extinction coefficient times the concentration times the path length. So let's just wrap this up with pointing out how Beer's law points to the linear relationship between absorbance and concentration. So if we have the equation for the slope-intercept formula of a line, we have y equals mx plus b, and we have our equation for Beer's law, absorbance is equal to the extinction coefficient times the path length times the concentration. We can see that the absorbance is equal to y, that's our dependent variable. Our slope is equal to the extinction coefficient times the path length. Those are two constants, right? And our concentration is going to be equal to our x. That's our variable, all right? We can change our concentration. And Beer's law assumes that the line goes through the origin, so our y-intercept is 0, where in our equation it's b. So for these equations, we can see the linear relationship between the concentration and absorbance. This is one of the fundamental concepts communicated in Beer's law and why it is so very useful. So how is Beer's law used? Beer's law is used to find out, in some instances, if athletes are using banned substances. This is done by finding out the absorbance of their blood, and the reason why it's used is because the absorbance of their blood should fall within a certain range. When the absorbance of the athlete's blood sample falls outside of the range, the testers can infer that there is an excess concentration of a particular substance in the athlete's blood. In short, it is used to find out if athletes are doping. And we all know that there have been many circumstances as of late where athletes have been found to be doping. It has also been used extensively in our summer internship research to find out the absorbance of various compounds dissolved in various solutions and identifying where light is being absorbed by these different solutions. So thank you very much for listening to this presentation. Hope it was helpful. And so thanks for listening, and have a great day.